So you probably already have the idea. What is a function? A function is a block of code that has a name so that you can execute that block of code just by using that one name. We've already been writing functions in this class. You know, want to calculate the surface area of a circle? You write a function that'll do that. You know, that way, if you have to calculate the surface area of 100 circles, you don't have to copy and paste that code 100 times. You just call that function whenever you need to, preferably in a loop. So that's known as modular programming. You break a program up into smaller, manageable functions or modules. If you took Donna Wilson 1113 class, a textbook called them modules. I like the term function because that's what C uses. Java uses the term method. C++ also uses the term method. That's when we are creating classes. We're not creating classes yet, so everything is still a function. What a method is it's just a function that is attached to a class. So, what is a function? It's a collection of statements that perform a task. So every function should have a name and it should have a body. And then inside parentheses it may have a parameter list, right? If the function doesn't need any data to be passed to it, it won't have any parameters, and you'll just have, empty set of parentheses. But if it does need, data passed to it, a string, a couple of ints to perform a calculation, something like that, then those parameters would be would be defined between the parentheses. When you're passing data into a function, that data is called arguments. When you're writing the function, the variables that receive those arguments are called parameters. So the motivation for modular programming: improves maintainability, simplifies the process of writing programs. Why do we say improves maintainability? You can test that function. You could even write a framework that all it does is call your functions and test them, even if it doesn't do anything else useful. And then every time you make a change to your program, you call those tests, make sure it works. It's a block of code that you could inspect and make sure it works, and it's not part of a huge morass, right? So you don't write a main that's 10,000 lines of code. Instead, you break it up into functions, and each one is a manageable chunk of what you want your total to do, which should simplify the process of writing programs. You could have several people on your team. You say, okay, you need to go write functions A, B, and C. You're going to write the stuff that displays the information on the screen, so you're going to write some more functions. You're going to write the code that saves it to files, so you're going to write some functions. You define those functions, you send those programmers out to do their work, and all is good. So instead of doing this, int main, statement, 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 you define some functions. Function 2, function 3, function 4. Now this is kind of dumb because main would not have statement, statement, statement in it. This book is making a mistake. Instead, it would call function 2, function 3, and function 4, right? Nothing is calling those functions in this example. But anyways, you break it into blocks. Conceptually, you're not just going to arbitrarily go, okay, I want 50 lines of this in this one, 50 lines in this one. You break it conceptually up. Get input data, save to file, perform calculations, that kind of thing. So defining and calling your functions. The function definition are the statements that make up the function. The function call is when you invoke it by name. So you have to define your function. Some texts call it a function header. The function definition needs a couple of things. It needs a return type. If it's not going to return anything, it's void. That's a return type. That means nothing. In Python, you didn't define a return type. You just gave it a function name. And Python is kind of loosey-goosey. It's not really strongly typed, so that was fine. But in this language and in a great many others, you do have to define the return type. You have to tell the program whether it's going to be returning a double, a string, a float, or nothing at all. But if it's going to return nothing at all, it's a void function. Then, after the return type, you have to give a name to the function, right? Otherwise, it wouldn't know how to invoke it. And then a parameter list. If there are any parameters, they'll be defined within those parentheses. If there are no parameters, you'll still have the parentheses, just nothing between them. And then it needs a body within curly braces. If there's no body, there's no reason to write the function, right? It doesn't do anything. Now, when you're just kind of initially speccing out your code, you might just write dummy functions. They have the names that you want, but all they do is print something, right? You know, just to show that they've been called. You don't have to implement the full functionality of your program of each step as you go. You could just, it's known as stubbing it out. I'm going to define all my module names, and then I'm going to write the code that calls them, and then I'm going to make the functions actually do something. So you're building a framework. You don't have to sit down and write a program from top to bottom and have it all work at every point. That way you could have multiple people working on it at the same time. You're going to be writing these functions, but I've already provided the skeleton for you. I've already defined the headers for the functions. So here we go, main, int main. That's the return type, that's the function name, that's the parameter list. We have a body of code between the braces. So if a function returns a value, it must be indicated. Int, float, string, long, whatever. If the function does not return a value, its return type is void. Right? Print heading. It's not going to return anything, but it is going to do something. Now, if you wanted to, you could make absolutely every function return something, like a Boolean value, true or false. Did I succeed? Did I not succeed? And if you know it's going to succeed, you just return a true. But that's a bit extreme, because I'm not going to be checking the return values, you know, of everything. In the 80s, like the first, it wasn't a virus, it was known as a worm. The first worm that infected like thousands of systems. What is a worm? It's a program that moves from computer to computer over a network without requiring the user to run anything. If your program does require the user to run something, that's a Trojan, right? Trojan horse program. But a worm will spread itself automatically via network connections. That's also different than a virus, right? A virus has to attach itself to a program. And then when that program runs, it infects your machine and hopefully has some way of being communicated to another one. So those are all related concepts. But the first worm was written to infect Unix systems, and it exploited a flaw in the SendMail program. The SendMail program is the one that sent mail from computer to computer under the in the Unix operating system. And I'm sure that if you install Linux, there still probably is some vestigial SendMail function. The format, the protocol that it followed is still used today to some extent. You know, how do things email work? You know, you got to specify the header and the date and the body and the subject and all that stuff. You know, SendMail would have created. But there was a flaw in it, which is that if you sent too much information to SendMail, it would overwrite past the end of the buffer. And I already talked about how a character array ends in a null, right? And like you might have a character array that's 80 characters long, and maybe you thought that was long enough for anybody's name. But then you sent somebody email that instead of having only 80 characters long for a name, it had 800 or 8,000. You know, broke the program, caused it to overwrite some memory, and then you could make the computer do something else. So that's known as a buffer error, a buffer overrun. It's a very common, or at least it used to be a very common exploit. So the SendMail program, what it would do, or the SendMail worm, you know, it would infect a computer, and then it would look in it for other computers that people had sent email to. And then it would send infected email to those computers. And then those computers would examine, you know, email that had been sent, and it would infect them. And this was like in 86, 87, something like that. People had really never experienced anything like this before. Where was I going with this? Oh, okay. One thing that was curious about the program is that although it was very complex, every function, even if it didn't need to, returned a value. So when people ran, you know, what's known as a decompiler, something that takes an executable and turns it back into C code, they're kind of going, that's weird. Why did he write it like that? Yeah, it's not really pertinent to what we're doing. We're not going to write every function that returns one. What was interesting is the guy, Robert Morse, who wrote that, was a student at Cornell, I believe, and his father was the head of the NSA. The NSA, as you know, very big in computers and stuff like that. So he managed to take down, not intentionally, you know, just about every computer that was attached to the fledgling internet at the time, which was, you know, all the campus computers in some businesses and some defense contractors. And he hadn't meant for that to happen. What it was supposed to do is just provide a map of every computer that was on the internet. He wondered how big the internet was. And so it was supposed to, supposed to get to a computer, infect it, and then, send those messages out and email, him saying, okay, this computer, is on the internet. But it didn't stop at that. What it did is it created another process, and it created another process, and it created another process, just like running itself over and over and over until it used up so much memory that it crashed the system. If it hadn't done that, then a lot of people would never have noticed that there was this program, that was moving through their networks. But so it brought down the entire educational internet, right? The defense contractors who used the internet at the time. And so can you imagine calling your dad up and going, oh, Dad, I broke the internet because your father's the head of the NSA. Okay. All right, enough history. Every function can return either something or nothing. To call the function, you give it a name. And then if it needs to accept any arguments because it has defined parameters, then you put them between the parentheses. When it is invoked, when it is called, the program will execute the body of the call to function. When the function terminates, execution resumes at the calling function point of call. Now that was actually kind of a big deal when it was first invented in the 50s or something like that. The idea of having code modularized so that you can invoke it by name. Until then, you just kind of had go-to statements that would go to a chunk of code and then run it, and then it was supposed to go back to where it came from. But if you wanted it to be run from several different places, you had to figure out a way to make it go to those different places. Anyways, it was pretty nasty. You could have a function that calls itself, right? We've already talked about infinite loops. This is almost an infinite loop. It's different than an infinite loop. We might actually type this in just because it's kind of fun. But look what happens. We have a function called call me. Let's make it, print something. Call me maybe. All right, there we go. So main, when it runs, invokes the call me function, which runs up here, prints out a message, and then it calls itself again. So it runs up here and prints it out and it calls itself again. It will eventually crash. The program will crash. And the reason why is there's something called a call stack. A call stack is how the program knows how to return. And I'll show you what I mean. What if I had this function here, void A. Maybe we ought to actually be typing this stuff in, but I'll give you the examples first. And then you had another one called void B. And when you called A, it called B, right? So down here, when you invoked A, how does it know how it's going to get back, right? It runs up here. It starts running that. It runs up here, does whatever B is supposed to do. There's a return statement here. How does it know where to return? Seems obvious to us. Oh, I'm going to return there. But the computer, the compiler, has to know where to return. So what it's doing is in some other block of memory, it's keeping track of all these calls. It's called a call stack. The function that we are in is called main. And then it invokes function A, right? But when it jumps in there, it keeps track of the address it was, some kind of address in memory, where that statement was, whatever, And then it calls A, and then A calls B. So it invokes B, right? But it has to write down what address it was at before it did that, and who knows, this may be in a different area of memory. And then when B returns, it goes, okay, I know that I should have gone back to 660. So it comes back here. That is removed from the stack, called popping off the stack. And then when we're going to return from A, it looks to go, okay, I need to return. And where am I going to return to? I'm going to return to that address, which is right there. And then it runs call me. Call me is where things start to go haywire. Why? Because, okay, we were at this memory address. It runs up here. It calls call me. Call me does something and then calls itself again, which was at, a different address, 9,000 or whatever. And it calls call me again. which is at address 9000, and it calls call me again, which is at address 9000. You can see what's going to happen, right? It keeps tacking these on to that area of memory until it fills that area up. Can't run anymore. And that would be fun enough, but let's actually do it. Just so we can see what it looks like. So new project, boilerplate. I already did a new project. Why am I making another one? Because I can't see my Solution Explorer. New source file, add new item, CPP file, the usual. # include IOStream. # include string using namespace std. Int main. System pause if you're using a Windows PC. Return 0. Okay, let's write some functions. Maybe just the same ones I did. So void A, and all he does is see out A called /n, end quote. Now, should I put it all in one line like that? No, I ought to break it up like this. I ought to put, you know, that on a line, that on a line, that on a line like that. It's easier to read. But I'm going to go ahead and do it like this. It's legal, unlike in Python, where everything had to be indented just perfectly. Okay. If that messes with you, go ahead and space it out the normal way, right? Now let's make another one. Void B. That does the same thing. I could just copy and paste that text, but it's going to see out B called /n, end quote, semicolon, end curly brace. And I'm going to write a function void C that calls both A and B. Void C, this one I am going to space out correctly, I think. It invokes A, and then it invokes B. That was supposed to be void, not voice. And then before that, actually, before the calls to A and B, I'm going to see out C entered /n, and then after those calls, I'm going to print C exited, or C returned. C returns. All right, I know that's quite a bit of typing, so I'm going to slow down there for a second. Now down in main, I'm going to call C. So right here in main, first line of code in main is just going to be a call to C. And it's C's responsibility to call A and B. And who knows if it's going to work? I'll rebuild it. Check the error list. No errors. Good deal. Going to run it. Wish I would keep track of these things between runs. All right, so I ran it. Main called C. C called A. Now A didn't call B. A really returned, right? And then C called B. And then C returned. If we added some return statements, it would make a little bit more sense. I would have to space it out a little bit. But I don't mind doing that. Now that I've got the main structure together, and then I'm going to walk around and make sure that everybody's good. I'm going to first modify the B function. I want it spaced out like this. Go ahead and put that on its own line. Go ahead and put that on its own line. But underneath it, write a line of code that says B returns. So C out, arrow, arrow, beginning quote, B returns, backslash n, end quote, semicolon. And do the same thing for the A function. I shouldn't have to show you how to do that. I mean, I will. But as soon as you've done it for B, do it for A. All right. So I'm spacing it out more nicely so I could tell what I'm doing. So underneath the line that says A called, I'm going to put C out, arrow, arrow, quote, A returns, backslash n, end quote, semicolon. Now when I run it, it's going to show all of that stuff. It's going to show it as it enters and exits each function. All right, so C was entered, it called A returned, it called B returned, and then C returned. And we can see what it's doing. You know, it's hopping into it, and it's returning back out, it's hopping in, and it's returning back out. Good time for me to make sure that everybody's doing okay. So we're going to write a recursive function. We're going to do that call me function. Void call me. And all it's going to do is C out, call me, enter, backslash n, end quote, semicolon. And then it's going to invoke call me again. And I'm not sure how long it's going to have to run before it runs out of stack memory. And we're going to find out. What did I do wrong? I did something dumb there. I never invoked it, right? So above the pause call, right here above system pause, do a call to call me. Invoke call me. All right, looks like an infinite loop, but it's not. It's entering the function over and over and over, and it's never exiting the function. And then it says unhandled exception stack overflow. Stack overflow means that it ran out of memory in that call stack that I was describing for you. I wonder how many times it had to repeat before it crashed. We're going to find out how many times it has to repeat. The easiest way for me to think is to use a global variable. So I'm going to break the program, and then I'm going to try to stop all of this that it's doing here. Hope that can get it to stop working. Come on. Stop. All right, come up to debug. Stop debugging. All right. Okay. So I'm going to declare a global variable that call me is going to use. I'm not sure what I'm going to call it. Int calls. We're going to start it out equal to 0. I'm going to put a comment that this is a global variable. If I was cool and awesome, I would put it in its own namespace. I'm going to leave that alone just to make the code a little bit easier. Now, as soon as we enter call me, we're going to increase that variable. So the first line of call me should now be calls plus plus, right? Calls plus plus. Then the next line of code, or maybe even this one, should print out the number of calls we've had. I'm just going to put it on its own line to make it easier to type. C out, arrow, arrow, calls equals, end quote, arrow, arrow, calls, arrow, arrow, E and DL. Now run it, and we're going to see how many times it's allowed to call itself before we run out of memory. It's taken a while. If I minimize it, it actually runs faster.
I think I saw like 4,803 for the last time.
Yep, mine got to 4,802, so yeah. 4,803 would be, you know, it didn't get to print the last message, but I'm sure that it actually executed it. So, okay, yeah. It was able to call itself. We were able to go in 4,800 times. Imagine a room that had a door that led back to itself, right? And you just kept going into that door, right? We did that 4,800 times.
So a door frame in a room?
Yeah, like the game Portal. You had a portal. Yeah, and the hole let you drop into the room, and then you went through the portal again, and it kept dropping you in the same room. All right, stop debugging now. So just go up to the debug menu. Stop debugging. We need to take like half an hour and actually work on debugging. What you do in debugging usually is you step through your program line by line. And the way you do that is you set a breakpoint. Your program runs until it hits that breakpoint, then it stops, sitting there waiting for you to do stuff. And you can move your mouse over the variables, and it'll tell you what each variable's value is. It's got a variable list down here, so you can see what all the variables are currently, you know, defined and their values. And then you can click a button or something, and it'll go to the next line in the program. And you click that button again, it'll go to the next line. And you do that so that you can see the program as it executes. Very, very important skill to learn. We do not give it enough importance in these classes. I should have been having y'all do that since like day 3. So we all good? Anybody getting syntax errors? We have to get rid of this call me call, right? Or else it's going to crash every single time we run it. So down here in main, wherever we call me, comment it out. I'm just going to put a comment here that says recursive function crashes program. Now, like I said, recursion actually has a use. You can write functions that call themselves and actually do good stuff. But what you have to do is provide it a way out. You have to have something that has a return statement at some point. Sometimes it's going to recurse into itself, but sometimes it's going to return. Because if there's no way to return, it just keeps burrowing into itself and it never stops. So main can call any number of functions. Each one of those functions can call other functions. But the compiler must know the following about a function before it is called. It has to know the name, it has to know the return type, it has to know the number of parameters and the data type. Now these functions are pretty simple, right? Because they don't take any parameters. And they're just all defined as void. But you still have to have them defined. If I took all this stuff and cut it, everything above main, if I cut it, all the way from using namespace, everything under using namespace, all the way down but not including main, cut it, and let's put it in another programming file.
Everything below using namespace?
Yep, everything from between using namespace and int main. Cut it all. And then go over to source files and create a new CPP. Don't give it the name source.cpp, right? Because we've already got one called source.cpp. So cut them all, go to source files, do add new item, and make a new CPP. This one's calling it source 1. That's kind of lame, but I may run with it. We should be giving these program files good names. Now I have a fresh file here. Now this isn't going to work. Why is this not going to work? Because it doesn't know what cout is and everything like that. So I'm just going to flip back over to source, and this isn't really necessarily the best way to handle it. I'm going to flip back to source, and I'm going to copy my boilerplate up here. Using IOStream, using string, using namespace, and I'm going to put that into my source 1, or whatever you called your new CPP file. That's at least going to fix those errors.
So why didn't we do that in the first place? Just copy
I didn't want to. what I did is I cut some stuff and I copied some stuff, and I didn't want to try to figure out how to do that all in one fell swoop, if that makes sense. Yeah. Otherwise, I would have had to copy, paste it, and go back to the other one and cut certain stuff. What I really should do is I should put this stuff in a header file, and maybe we'll play with that. We're going to have a header file sooner or later, because even though this looks good and this doesn't have any errors, source.cpp has errors now. It at least has one error. It doesn't know what C is. It doesn't know what kind of parameters that function takes. It doesn't know what kind of data it returns, because we don't have a prototype defined for it. So what we're going to do and what we should do are two different things. What we're going to do is we're going to define a prototype and just stick it above main just to get it working. But then we'll probably move it to its own header file. So void C, and C doesn't take any parameters. And then since it's just a prototype, it doesn't have a body. So void C, parentheses, in parentheses, semicolon. That's enough to get it to work. I hope. And you Java programmers, this will kind of bug you to have to do, because you didn't have to define prototypes. All right, seems to be working. The program is working just as well as it did before that call me business. Here's what we really ought to do. We ought to take both of these includes and that prototype and put them in a header file. And presumably, we're eventually going to have more prototypes, right? We could have prototyped A, and B. The only reason we didn't prototype those guys is because they were defined above C. But it's kind of lame to have to rely on those things. So why don't we go ahead and prototype those as well? And then I'm going to need to do walkabout, because I know that we're making a lot of changes. Go back to your original code with the main and prototype those other ones as well. We just had two more functions. Void A, parentheses, in semicolon. Void B, parentheses, in parentheses, semicolon. Good enough. I'm going to make sure that this works before we take the next step, which is to move some stuff to a header file. All right, still working. Bless you. So, just to switch between the two, our new source, which I called source1.cpp, has our # includes, it has the names using namespace, and it has those functions we wrote. It even has the call me one, although we're not using that one anymore. And then our original one, those functions are now gone, but in their place are the prototypes. All right, guys, the error I saw the most, and I'm going to make this change super fast, so hopefully you don't get to see what I'm doing. You probably saw it. Anyways, is I would run it, it would give me an error. There were build errors. No, of course, I don't want to try to run the old version. And I look down here, I'm getting a warning about my call me function. It's telling me that it will call Stack Overflow, so the compiler is being nice and telling me that. But here's the real problem. Main is already defined. You can only have one main. We have two source code files. Only one of them can have a main. So I need to decide which one should not have a main. And I like main being in source.cpp, so I'm going to go to source1.cpp and delete it. Now everybody's got this working now, so you don't need to do that. That's the change that I made in order to illustrate the problem. Just remember, you're only allowed one main, and if you get this error here, main already defined in source, you just have to go find one of them and remove it to get it to work. Alrighty, now what if we have a whole bunch of code that needs to be able to call A, B, or C? Not just main, but we may have 20 other source files that need to call A, B, and C. I don't want to have to define those prototypes in every one of those source files. I want to put them in a header. So all I have to do is # include my header. So what I'm going to do next is I'm going to cut all of this stuff. I'm doing it in source.cpp. I'm doing it above main. Let me Get some of this stuff. Cut all of this stuff. Include IOStream all the way down to void C. All of our usings, all of our everything. Cut it. And then go back to source files. And you know how every single time we've added a source file, this time we're going to add a header file. So after you cut, go to Add, New Item, and choose Header File. And give it a, well, I'm going to leave it header.h, but we're getting ridiculous with our names here. We ought to be giving them good names. But I'm going to stick with header.h. I can remember that long enough, right? Okay. And paste your # include and your using namespace std. That should be in your header file now. It should not be in source. But source doesn't know about any of this stuff anymore. We need to add and include to get that header file back in. So here's my header.h. It looks like that. It's got my # includes, my using namespace, and by the way, that's really tacky to throw using namespace std. If I was being rigorous, I would take that out and I would always just use std : c out and cin. But go back to source.cpp, and the way we fix these errors is to include our new header file. # include. Now we don't use the angle braces this time. Instead we use double quotes. # include, not debug slash, header.h, which it's trying to offer to do. And there. What happens is every time it runs, or excuse me, every time it compiles, the compiler goes and imports all the stuff from header.h and puts it in this file so that it can compile successfully. Yes, sir?
So why would you want to use something like that? Why couldn't you just like copy and paste everything into like?
Well, what happens when I change function C to require a parameter or to return a different data type? If I have 70 source files, I call that function, I don't want to have to go and change them all. I'd instead want to just change the header file. And then when I tried to recompile it, everything that was calling it with the old syntax would be flagged, instantly. I wouldn't have to go and change them all because maybe only 5 out of those 70 files really use that function. So header files are useful for that purpose. They make it really easy to reuse code. And sometimes you're going to get code that you don't even have the source code to. You only have the libraries. You'll have a header file, and then you'll have a .lib or .obj. And so the header file is going to be the only way you know the names of the functions that are in that library or how to call them. That makes sense? Okay. Very good question. All right. Since I've got that header file declared and being used, I may as well also use it in source1.cpp. Right? We have that header file. So I'm going to go to source1.cpp and delete all my # includes and all my using namespaces, and instead I'm going to include quote, and I'll tell you why we're using quotes rather than angle braces in just a second. So now that should be the top line of both of my CPP files. So what do you put in header files? You put constants. You put prototypes. Later on, we will be putting class definitions there. Anything that you want shared by more than one file needs to be put in a header file. Java does not have the idea of a header file. Java figures it out based on your .java files. The compiler goes, okay, I'm going to open all my .java files and just figure out where all this stuff is. But that's because it was written, 15 years after C++ was invented. Alrighty. Is it running for everybody? Wave your hand if we've managed to break your code. I'm not trying hard enough and we haven't broken it. Working for everybody? Okay. I just want you to have the idea of the header file. Even though we may not use it for the next week or two, we're certainly going to start using it when we talk about classes. One more thing about functions that I want you to know. And this is going to be the reason why we talk about pointers and references. And you may remember this from Python. Maybe your instructor hammered on this. Maybe they didn't. But write a test function here. Void, now let's call it change me. And it's going to take a parameter, a temporary variable, t, whatever. And all it does is it sets t equal to 100. And we could add the return statement, but as you know, if it's a void function, you don't need a return. Now, why do I write that? Because I'm going to create a variable, and then I'm going to call change me on it. So let's create a variable. I don't know what I'm going to call it. It's going to be called Fred. I'm going to give it a starting value of 1. Then I'm going to call change me, and I'm going to pass Fred in as an argument to fill in that t parameter. It bugs some people that these aren't named the same. When you call it Fred here, you ought to call it Fred here. You call it t there, that's because they are completely different things. This is a variable, but this is a different variable. Just because it's defined in a parameter list doesn't make it a variable. The parameter list is just a series of variables that are defined between parentheses that get filled in with the values that you pass to it. So we could pass in a whole number here. We could pass in another variable. It could coincidentally have the same name. It could have a completely different name like this one does. Okay, and then we're going to see out the value of Fred. Fred equals, end quote, arrow, arrow, ENDL. What's it going to print? Is it going to print 100? You Python programmers may know that it's not going to print 100. It looks like it's gonna. Why do I say that? Because when we call change me, it passes this variable Fred up here, and so this now contains the contents of Fred. And then we turn around and we set that equal to 100, and then we return. So when we get back here, I think that it ought to contain the value that it was set to. But do you remember what I just said? They are separate variables. They are not the same variable. That's why I gave them different names. Fred is not equal to t. C, C++, Java, and Python do something called pass by value or pass by copy. This copies the value of Fred into t. They're not the same variable. They're not the same memory address. They're completely different memory addresses. They're completely different variables. So t is just a copy of Fred. And it can do whatever it wants to with t, right? It's just like I gave you a sheet of paper that was a photocopy of my signature. You could scribble it out, put whatever you wanted on it, but I still have my original document, right? You just have a photocopy that you're messing with. So that's pass by value. It gets the value, or pass by copy. It's called both things. It gets the copy of that. What if you wanted this function to really be able to change that value? There's a couple things you could do. But what have we done already that would let you do that? How could you get a value out of here back to here so that we could print out 100 rather than 1?
Change it from void to
We could return it. You're right. That's one thing we could do. Don't necessarily make this change. But if I went up here, I did int, and then I did return t, right? And then down here, I did Fred is equal to change me. I'm going to undo all those changes, so don't make them. But that worked just fine, right? We passed a 1 in, but we set it equal to 100. We returned it. It got copied into our Fred variable. That's one thing we could do. You can return your modified value. And just as promised, I'm undoing all my changes. Here's another thing you could do is you could define it as a global variable, right? Int t. You could then not pass it in as a parameter, you know, and everything would just use t. You would see out t rather than Fred, right? Something like that. Global variables are tacky. Using return statements are great, but what if you had 2 values that you wanted to be able to send back, or 10 values, or 100 values? You wouldn't make 100 global variables. Actually, what you'd probably wind up doing is storing them all in an array and passing them. But if you had to return 2 values, you can't, unlike Python, do return x comma y and have 2 returns. You can only return 1 value at a time. And that's where the idea of references and pointers come in. References and pointers let this guy not just get a copy of this variable, but the actual variable itself. So instead of me handing you a photocopy of the data, he actually yanks the data, does some changes to it, and then, you know, passes it back or whatever, so that when I look at it again, it's been changed. Now this chapter doesn't hit pointers and references right yet, but I'm bringing you to that concept. Why this variable scope? We've already talked about scope, right? If I have a variable called x here, I can't print x out from here, right? Why? Why can't I print out x here? I just called change me, it declared a variable called x. Maybe it set it equal to 1, something like that, but I can't print it out. Why? Yep, I heard the magic words. It is local to change me. It is not a global variable, it's local, meaning that it's only available between the braces in which it is defined. Oh, my brain just had a memory gaps. Where was I going with this? Holy moly. Oh yeah, I remember. So t is also just a local variable. It's just defined between the parentheses, but it's still only applicable within these braces. So when we pass a value in, t is a variable just like x is. You can make any changes to it you want, but it's not available down there. Hope that makes sense. I hope that's a good enough explanation for why. We can change that thing all we want, but it doesn't change the original data. Fred still has his original value. I'm going to delete that line because it doesn't work right. I'm also going to delete this x equals 1 because we don't need it anymore. So when you invoke it, the compiler has to know the name, it has to know the return type, it has to know the number of parameters, it has to know the data type of each parameter. The way we've been getting around this in this language, in this class mostly, and in Python was we always defined our functions above our calling code, right? Made it easy. But if you're going to spread your functions about in different CPP files, or if you don't want to be so particular in your order, you have to define prototypes. And the best place to put prototypes is in a header file so that all the CPP files in the project have access to them rather than just copying them as you need them, which works. So when you submit this project, you're actually, when you're done, if you zip the whole project, great. If you're just in a habit of sending me source.cpp, just give me all the files. Give me the header file and the CPP file. I'll mention that again when it's time to upload it. All right, function prototypes. Well, what do you know? How do you notify the compiler about the function before you call it? You place a function definition before you call it. You know, you put the function up at the top of the program. Or you use a function prototype, which is a declaration without the body. Right? We had void a parentheses in parentheses, but we didn't have a body there. We just had a semicolon. We're kind of making a promise that later on in the code we're going to actually define the body for it. So here's the header, you know, and it's going to have a body. It's going to do something. And here is the prototype for that. The prototype is just a header followed by a semicolon. And in reality, it'd have to be reversed, right? Prototypes go up at the top. So here we have some function prototypes. This is saying that somewhere we have a function called first, and somewhere we have a function called second. Maybe in the same file, that's where they're going. It's actually underneath this code. It could be in a separate CPP. It could be in a library, a DLL. That's what a DLL is, a dynamic load library. But anyways, this compiler has to know how to call them, so we had to have our prototypes there. Once we define those prototypes, that code actually has to be available, whether it's down, you know, below main or in another CPP file. And that's what they showed here. They put the actual function below main. So general rules, you place your prototypes near the top of the program. Do you put it above the pound sign includes? Nah, put them underneath the pound sign includes. The program must include either the prototype or the full function definition before any call to the function. Okay, you could do some really squirrely things with header files if you wanted. You could put code in it. You could define a function, you know, it or void d parentheses. I'll demonstrate this. Please do not do this. But you could. I could go up to my header file and write an entire function here. And then when I compiled source.cpp, it would bring that function in, right? Because it's part of the header file, and that's what #include does, is it copies all the text out of the header file in it. But the problem is do you remember when we could only have one main? We can also only have one D function. So if that header file is shared between more than one .cpp, this won't work. You might be able to squirrel your way around it. But you generally don't want to put code inside your header files. There's one exception. When we get to defining classes, there's two ways you can define a class. One is you can define the class in the header file and then implement the code in the CPP, or the other is you could define the class entirely in the header file. We'll get there. I'm going to delete that, but you can put anything in here that you wanted to put in here. And someday we'll do that. You could even put a main right in the header file, and then your source.cpp, all it would do was include that file and not even have any other code in it. That'd be dumb, but you could. All right, I said it wouldn't work. I'm going to go ahead and compile it and see if I get an error, like I said I would. Yep, there were build errors. What are the errors? It says that we already have something called D. Gives you a more specific error, right? C loves to give you these errors that you can't comprehend without knowing a lot. Void, underscore, C decal. You go, what's a C decal? But, you know, you could Google it up. That's just the way that some functions are defined. Decal, C declaration. There are other ways that functions can be declared besides C decal. That's way beyond where we're going with this. Sending data to a function. Between the parentheses, you define a parameter. And then when you call it, you can call it with, you know, some arguments. And we just did that, if you were typing along with me. When we did change me. I don't know if you made that change to your code. But we are passing data into it, right? We could do something with it. We could print it out. We could calculate the radius, whatever. You know, I'm always doing circles, you know. But double calc area or calc underscore area, and it takes a radius as its input. And what's it going to do? It's going to return pi r squared. So 3.14159 times radius, or whatever. I know that we could get pi out of the CMath library or something like that. But it bugs me because it's defined in one library in Microsoft C and it's defined in another one in the standard, you know, GNU C or something like that. So I'm just going to define it like that. Anyways, okay, so if I want to calculate the area of a circle, I can. Let's ask the user for the area. See out, what is the radius? Space, end quote, \n. I forgot the \n before I did the end quote. And let's read that into a variable. We don't have to call it radius, even though it's called radius up here. Maybe I'll create a variable just called r. Double r, and then cin into r. Now let's get that area. We have to call this function in order to get the area, but we need something that will accept what it's returning, right? If it's returning something and we're not storing it anywhere, we shouldn't have returned it to begin with. So double area is equal to calc underscore area. And we need to pass in r as an argument to fill this radius parameter. And we could print it out. See out, you know, this is, we've already been doing this kind of code. We're just talking about the specific terminology now. Area is, end quote, arrow, arrow, area, arrow, arrow, ENDL. And there were errors. What'd I do wrong? Build, rebuild solution, so I get a good error list. It's still complaining about D. I thought I deleted it from the header. Maybe I never say, nope, it's still there. All right, my mistake. I told y'all not to type it. I hope you didn't. Rebuild solution. Run it. All right, it's asking for the radius. My circle has a radius of 1, so the area is 3.14159, which is correct, right? Because 1 squared is 1, and then you multiply it by pi. So let's take a gander at that slide one more time. I know that maybe not everybody's had a chance to type this in without errors. I'll create the Dropbox and then I'll wander around and help y'all. But what we're doing here, we're sending data into the function. So the values passed in are called arguments. The variables defined in the function that get those arguments are called parameters. So radius is our parameter. R is our argument. R, matey. And their example, display value. All it does is accept a num, and then it prints out the value is num. When you declare the data, you also have to give it a type. So I could not pass a string to my calc area function, right? It needs a double, or it needs something that the compiler knows how to convert to a double. And we've already talked about it. If you have an int, ints get converted to doubles just fine, right? But if we made this int radius, the r was a double, that would not work just fine. It would have to round it down or something, you know, before it could pass that data in. So you define your parameter types, one for each one. You know, double, radius, comma, int, height, comma, you know, string name, whatever. You have to list them all. You can't do like you can down here. Remember, we don't use the syntax very much, but you could do int x, comma, y, comma, z. You can't do that in there. You have to give a specific name and a specific type for each one. All right, let's make a Dropbox. We'll be done for today. So we will have a little bit of homework for this topic. C++ functions. You're going to write some functions. You're going to place all your functions below main. So you can't cheat and get away with not putting prototypes. So you're going to put all your prototypes above main. Then you're going to write code in main that calls those functions. You don't have to make your program use CIN and ask for data. You can just pass in numbers, whatever you want. And then have main print the return values from non-void functions. If the function is void, you know, you're not going to print it out. So here's your functions. You're going to make a function called hello. It needs to have a parameter, which is a string. And it has no return type. And I'm going to be lenient and give you the function definition just for this one. So it would be void hello, parentheses, string, first name, right? And the functionality, the hello function prints a message saying hello, followed by the first name. And then there's another one called hi there. It returns nothing, but it takes two string variables, first name and last name. And this one's got several functions, but it shouldn't take you too long. And it's got one called times 9. It takes an int and it returns that number multiplied by 9. And we'll do more functions on Tuesday, so don't panic. You don't have to do this over the weekend. Take a shot at it, though. One called circle area. Well, what do you know? We've already written circle area just in our notes, except we called it area of circle, right? And then a function called counting, which uses a loop to display the numbers between 1 and 10. Just had to sneak loops in. All right, so that'll be homework that we got to do. Let me unhide it and make the Dropbox so y'all can scamper out of here. And we're going to need Dropbox LN, N as in Nancy, new folder, in functions, chapter 6. All right, refresh your Dropbox. It's there to upload into.
Source CPP, right?
Pardon me?
The source CPP.
Yeah, I want all of the source CPPs and the header file, please.